Sound is a type of energy made by vibrations. These vibrations create sound waves which move through mediums such as air, water, and wood. When an object vibrates, it causes movement in the particle of the medium. This movement is called sound waves, and it keeps going until the particle runs out of energy. Let's see how these vibrations travel with the help of an audio visualizer. To make an audio visualizer, you need hacksaw blade to cut your pipes, pair of scissors, pieces of pipes which I have already cut it down using the hacksaw blades, elbows, and a small piece of pipe which I have taken from the rest, laser, balloons, elastic bands, few small pieces of mirror, super glue, and a cylindrical object. You can use any object. I'm using a cardboard cylinder taken from my foil papers. Take your small piece of pipe, put a hole in it. Your hole should be in this way so that the laser fits into it. If it doesn't fit, you can wrap a sellotape around it. You can attach the elbows in this manner, attaching the second elbow similarly. Now these pieces of pipes goes into the test part of the elbow. Once they are in the places, you can wrap them with the help of elastic bands. So you can put the elastic band in this manner. Let me put the rest of this. Once the elastic bands are in its place, here comes the second part. So now you need to take your balloon and now cut the balloon from here. Okay, so cut the balloon from here and a perfect alignment, I can say. The laser is on the mirror, as you can see it. Now let's see how it works. So now we are going to see how this is going to work. So I'm going to speak into this and let's see. So as you can see, I can talk also and you can visualize my frequencies. To study interference pattern of light, we need these objects. Foil paper, we don't need that much foil paper, we'll just need a small piece from it. Stapler, few popsicle sticks which I have cut it down, I'll show it later. A blade, be careful with it. A pair of scissors and a laser. These are the popsicle sticks. They were whole, but I've cut it in this way, in a half part. And now we need to make a frame out of it. So we'll place the popsicle sticks this way and we will staple it. The frame will look like this way after stapling it together. Now we need a foil paper. We'll take a small piece of foil paper from it. Make sure that piece is smooth and doesn't have wrinkle on it. This is the piece of foil paper I took from the roll. Now we'll staple it on the frame. Be careful, you should not wrinkle the foil paper or tear it. So after stapling, it will look like this. Take a blade and be careful with it. With the help of blade, make first slit on this foil paper. Be careful, your slit should be as thin as possible. It should not be wide. Next to this slit, make another slit. Just make sure you are close to the first slit, as close as you can. Take your time. Don't hurry with that. Once this is done, the two slits will look like this way. Once the slits are ready, what we're going to do is use the laser and shine it on the slit. The laser should be shined in such a way that the laser passes the other side of the slits and we see image. Now there are two slits. What we're going to see is two images. Only two images on the screen. No, that's not going to happen. What we are going to see is there will be number of images. A bright dark band, and there will be whole number of such bands, and to see that we're going to shine the laser and turn off the light. Let's see what happens. As you can see, this is a monochromatic laser, a single colored laser you can say, and we're going to shine this laser on this slit. This is the way we are going to shine the laser on the slit. Now this is the interference pattern we are talking about. As you can see, a bright band in the center and consecutive dark bright band on the right and left of the center bright band. Now the question arises, why this thing happens? We have two slits, we should see two lines, nothing more than that. Why so many lines? It is due to we think that light travels in a straight line and it is a ray, but no. In 1672, Robert Hooke, an English scientist, suggested that light is a wave. Now in 1678, Christian Huygens derived a mathematical wave theory for light, and around 1800 a scientist named Thomas Young did this same experiment and showed the world that yeah, light is a wave. What happens here is light travels from the slits to the screen and they are in the form of wave. Now the wave have two parts, a crest and a trough. So they meet each other, as you can see in this diagram. So when a crest and crest or a trough and trough meets each other, they form a constructive interference which gives us a bright spot. And when a crust trough or trough crust meets, we get a dark band, that is destructive interference. To demonstrate scattering of light, you need a light source. I'm using a LED light source. You can use any light source which is stronger as compared to this LED bulb. Foil papers to cover this light source to make it narrower, glasses, sailor tape, small amount of milk, spoon. Now you can use a dropper also, a pair of scissors. Here we will make a colloidal solution in this glass. Pour some water, a clear water, and then add few drops of milk. You can use a dropper, I'm using a spoon. A little amount of milk I can say here. Mix the milk completely so that every part is mixed properly. Now this is your colloidal solution and it's all set to be used. I have made 5 glasses of colloidal solution, as you can see. We will set up our light source on this table here so that light falls on our solutions this way. The light source is set up. Now we'll use some foil papers to make a light source narrower. We are making it narrow so that we can see the scattering properly. As you can see, I have placed the foil paper on it here this way. Now the light is narrower and this is a white light, as you can see, because the sun gives us a white light, and we are going to observe scattering. Now we'll place a colloidal solution in front of our light source in this way. Now since the colloidal solution is white and the light source is also white, what we are going to observe is a perfect white light from this side, and it should be a white light as we know, but you can see I'm going to add more solutions here and you can see the color changes. It turns a bit yellowish. Now if we go on adding such number of solutions, you'll observe that the color of the solution, or you can see the color of the light, changes to yellow, and this is the same phenomena as the scattering of light. So when the sun is over our head, we see a blue sky because of the atmosphere is thin, but when the sun moves toward horizon, we see a red sky, as you can see it here. Now we'll add one more solution glass to this, and you can see it is a bit more yellowish and reddish mixture. You can see clearly here the color is more reddish. Now I haven't changed the solution's color. The solution, colloidal solution, is white only, but due to scattering of light you see this red color. Now what's happening here? The question arises. White light is made up of different colors, that is F.Y.B.Ed, violet, indigo, blue, green, yellow, orange and red. We see these colors when we observe a rainbow or when we pass a white light through a prism. Each of these colors which I indicated have a specific wavelength, where violet has a smallest wavelength, that is 400 nanometer, and the red has the longest wavelength, that is around 700 nanometer. And you can see here how these wavelengths are compared. When you observe a blue, we don't talk about violet because our color receptors are not so sensitive to violet color, so we don't see violet color, we see blue color. As you can see, the blue has smallest wavelength and the red has longest wavelength, and the scattering of these lights depend on the size of particle. The light with longer wavelength doesn't scatters much, but light with shorter wavelength scatters too much due to the size of this atmospheric particle. When this light passes through the atmosphere of Earth, there are atmospheric particles, small particles that can be gas particles, that can be anything. These particles affect the path of these light. They get scattered, they don't go through a straight path. In afternoon, the sunlight has to cover less distance in our atmosphere. So usually what happens is the light scatters and we see blue color. But in the evening, or when the sun is near the horizon, during the sunset or sunrise, the light have to travel larger distance and most of the blue colors scattered, and we don't see them. We only see colors with larger wavelength, that is red or yellow.